So in this video, let's derive the expression for the velocity of the rocket by counting the weight. And this is the velocity of the jet in the lab frame. Capital V minus small v. Capital V is the velocity of the rocket and small v is the velocity of the exhaust. The rate of change of momentum of the jet, the force acting on the rocket, is dm by dt into capital V minus small v. So we are taking into account the weight of the rocket. So we can write the expression by taking into account the weight of the rocket. So this is the weight of the rocket is taken into account. We have used product formula, and then here also we have written this one as dm by dt into v minus v into dm by dt minus mg. So this is rewritten, and then so on cancelling the terms, both right and left hand side, we will get m into dv by dt is equal to minus dm by dt into v minus capital mg. So this is the force due to the acceleration due to gravity. So on rearranging the terms, we will get dv by dt into dt, which is equal to minus v by m into dm by dt into dt minus integral of g into t. So here we have divided the terms by capital M, and then on integrating we will get v is equal to minus v log m minus gt plus c. At t is equal to 0, m is equal to m naught. So initial time mass becomes initial mass and the velocity becomes initial velocity. Now velocity v naught is equal to minus v log m naught plus c. Now this is the constant of your integration c, and its value is derived here. And substituting the value of c in the equation 5, we will get v is equal to minus v log m minus gt plus v naught plus v log m naught. So this is the value of c that we have taken from here. So on rewriting this equation, we will get v is equal to v naught minus v log 1 minus beta t minus gt. So here we can write capital M as the initial mass into 1 minus beta t. So this is the final expression for the velocity of the rocket, and which includes the initial velocity minus v, this is the relative velocity or exhaustive velocity, log 1 minus beta t minus gt. So here gt term is negative. Here time is the time of combustion. If the time is very very small, and then gt term will make a difference, and there is an appreciable reduction in the velocity of the rocket is observed. If the t is large, then the fuel burns at a slow rate and the gt becomes large term. So this becomes large, and the rocket may slow down, and even the rocket may not escape, and this may slow down the rocket and also stop the ascent of the rocket. To obtain higher final velocity of the rocket should have very higher exhaust velocity and also the high loss of mass. That is, the ratio of final mass to the initial mass should be very very large.